Okay, so I think that I can start.
Honoring Scotland.
Master Okay, so we can continue.
Okay, we resume session 2. Some regulations on the location of spaces. We try to minimize in the design the number of hazardous spaces. So we try to put together the storage tank with the process and the gas processing and transfer systems. We can try to do that as much as possible to minimize the number of hazardous spaces, including the fuel preparation room. The tank connection space, TCS, or cold box, as it is also known, cannot be located adjacent to machinery space of category A. Machinery spaces of category A contain vital machinery items and control equipment. The width of a cofferdam separating hazardous areas has to be at least 900 millimeters wide, width of 900 millimeters, and combined with insulation of class A60. The fuel pipes have to be at least 800 millimeters away from the site cell. I would like to point out with this opportunity that the storage tanks we ask to be put at a place of B/5 or 11.5 meters, whichever is less. Please be reminded that in the LNG carrier, that distance is significantly lower. So that means that the LNG fueled vessels are considered to be more dangerous than the LNG carriers who carry a whole load of cargo, of LNG cargo. It is a little bit strange, but this is what IGF code says. Also, the bunkering stations must be in the open space in the deck, separated with A60 glass bulkheads and sufficient natural ventilation. So the entrances and other openings are also regulated in the IGF code. You can read the relevant slide. And also it is desirable to have fuel tanks, a redundant number of tanks, not only one, but possibly 2 tanks to use in case of emergency, use the other one. it can be, for type C tanks, it can be accepted to have only one tank, provided that you have two tanker connection spaces. If you have two tanker connection spaces, which are critical, then you can have only one tank. But in general, besides the economy of scale, economy of scale is to build the largest possible vessel, the largest possible tank. So we like to have one tank, but it's better if you split it in two for reasons of safety, redundancy. Fire protection, in a nutshell, we like to have A60 class in the accommodation spaces and also A0 above the navigation bridge deck. Here is what we discussed about the A60 class bulkhead. What you see here looks like what you see in the picture with relevant insulation. This is what an A60 class division will look like. Examples of A60 class. Easy to find and expensive to install. Now, zone classification. You will hear expressions like this is zone 0. Zone 0 means that there is continuous presence of gas. Zone 1, it means that gas is likely to be in that zone, is likely to be. And zone 2 is an area that normally is not likely to have gas, but it might. Under certain circumstances, you might have. I would like to give you an example with, I don't like these definitions. They are very confusing. Likely, not likely. I will give you an example with a gas station. At the gas pump, at the gas tank, the gas storage tank, gasoline storage tank, yes, we have, for sure, we have vapors, we have problem. This is zone 0, ground 0, problem. At the pump, where you are standing and putting the gasoline in your car, is zone 1. It is likely, if you are smokers, you are not gonna smoke in that area, because who knows? Then, at the cashier's place, it is zone 2. It is unlikely, but if we have a leak, then gas will be there. Very unlikely, normally you're not gonna find it, but it might, under extreme circumstances. So this is an idea, an example. So you will see this categorization, but I felt it is better if I show you some examples. So zone 0, inside the cargo tanks and outside, because this is the primary and the secondary barrier. So the interbarrier space and the tank are zone 0. Continuous presence of gas, although here I would say that somebody might take it as zone 1. But in the rules, the interbarrier space, primary, secondary, we consider it zone 0. So inside cargo tank 0, between barriers also 0. Zone 1, outside the tank, surrounding the tank, like in this area, outside the tank, zone 1. Also, every vent pipe that goes out of the cargo tanks has a vent opening which, for a sphere of 3 meters diameter, is considered to be also zone 1. As an example, for a hazardous area, zone 2, is the area outside an airlock. So this is a non-hazardous space. This is a hazardous space. The communication from the hazardous to the non-hazardous is through an airlock. We don't just have a door. We have like a small room, minimum area 1.5 square meters, 2 doors. No, these 2 doors cannot be open at the same time. One is closed, the other is open, otherwise an alarm will sound, and this space is also ventilated with positive pressure. We cannot have ingress of dangerous gas from this area because the pressure here is higher than the pressure here. So the area outside the airlock is considered to be zone 2. No, excuse me, the airlock. This is the zone 2 area. Now, the two C-type tanks, we have this tank room, which we call it, how do we call it? Cold box. This is closed, two access bolted hatches which are bolted, and this, the yellow space, is zone 2. Here we don't have gas, presumably, but it is zone 1, because we might have leakage from this where it's zone 0. So zone 0 for the cargo tank, zone 1 here because we might have leakage, maybe a valve. From here we have valves coming out. Maybe there is leakage from the valve. So here we have zone 1, and outside, exactly outside is zone 2. It takes some time to get used to it, but category classification is important. For what reason? We said for the equipment, to see if it satisfies international electrical code. Even the ventilation fans have to be special, non-sparking type. Ventilation. There is a need for continuous ventilation. I would say positive or negative. No question. The ventilation in this space, in the tank connection space, should be positive or negative. Should be negative. If we have gas coming from outside, outside is a gas safe air. So 30 changes an hour is the requirement for the ventilation of the cold box.
I'm sorry.
Yes.
Is the classification of zone is based on IEC guidelines, isn't it?
Yes.
Is it also same applied to LNG fuel ship as well?
Yes, of course.
So, but how could you apply the bunkering area? Have you read the ISO recently? The guideline that they're supposed to classify this
Yes,
safety and security.
ISO will determine the binding.
Yes. Any practical thoughts of you?
Not only ISO, but also every class has their own guidelines on how to do the bunkering and how to design the bunkering station. But everybody refers to IEC. Everybody goes by the IEC regulation when it comes to categorization for explosion proof and protection of electrical equipment. The same is true for the fuel processing, fuel preparation room. Also, we need to have about 30 air changes per hour. So ventilation is important because even if we have a leakage, we need a certain concentration of natural gas between 5 and 15. LEL 5%, 15% upper explosive limit. If we have too much natural gas, we don't have enough oxygen, too rich of a mixture, no explosion. If it's not enough fuel, still we don't have any explosion because there is not enough fuel. Another very important consideration is a little bit operational, the so-called filling limit. We cannot fill the fuel tank to the top, 100%. It's forbidden because when we fill, we have the provision to have some expansion of the liquid if the temperature increases. The formula that we utilize to see up to what percentage we are going to fill is right here. And believe me, when I first saw this, I could not imagine that in a liquid it will make so much difference. It does make a big difference. Usually we expect the difference in volume to be significant for gases. But for liquids, yes, it is, also for liquids. Keep in mind that we cannot lose any fuel, it's very expensive, and the charterers will not like to have missing cargo for this reason. So we have the formula that says the percentage of loading has to be the filling limit, which for every tank everybody knows, 98%, very good, 98%, times the ratio of densities. There is a reference density divided by the loading density. To make it a little bit more clear, I like to do an example. So we load methane, pure methane. For pure methane, the loading takes place at minus 151 degrees Celsius, where the density, we can see from the tables, is 407 kilograms per cubic meter, with 0.98% loading, and the reference temperature. What is the reference temperature? Reference temperature, if we know nothing else, we take 45 degrees. So here, they don't tell us anything else. At 45 degrees, methane density is 360. So when we do this computation, we get 0.866. It's forbidden to load above 0.86, 86%. So we lose 14% of the space because we don't want to go up to the top and have a problem in case of thermal expansion. Yes.
The vapor space that is on top, is it just a non-saturated LNG or does it contain something else as well?
No, it's saturated. It's a vapor
Is
on
it
top of liquid. Vapor
just LNG,
phase.
nothing else?
Yes. Now, the new IGC code, and sorry that I mentioned IGC, but I believe IG will also have the same provision, says no 45 degrees. 45 degrees is a high temperature. So it's not very good for the ship. It says, if you know where you're going to go, with the permission of the flag, you might use the maximum temperature expected during the voyage. So you want to go from, say, from Korea to Philippines, you take the predictions. They have modeled the ship, and we know the speed, the temperature of the air and sea throughout the year. So we go to the relevant month, we look into the graphs, and we find the temperatures. Maybe you do need a meteorological model. We are not only naval architects, we also become meteorologists. And this for that reason, because if we use, say, 30 degrees Celsius as the temperature, we will gain a few percentage points in filling the tank. Of course, the charterer wants to fill the tank to the top. Now, forget the charterer, this is for LPG vessels. If you carry LNG as fuel, you want to take all you can take. You want the maximum possible quantity because you compute the necessary volume on the basis of the consumption and the range. So you want to fill the tank as much as possible. So this is a very interesting and critical detail. Now, very quickly, I will show you some examples on fatigue assessment, primarily for tank A, type A, and type B. Of course, we consider typical details that are subject to fatigue. They are well-known structural designs, the supports, brackets, knuckles, structural discontinuities. We subject the vessel to various loading conditions with respect to the waves. The supports look like this. This is on the tank, this is on the hull. In between there is wood, so the support is modeled as a spring. This takes the weight of the tank and the fuel. Here is a model. We like to find the cyclic stresses because fatigue is caused only by stresses that cycle, that change. The constant stress, because the constant load of the vessel does not cause fatigue, only cyclic stresses. Also, there is a complication that in the beginning we have static friction. At certain point, when we reach the certain number, we are like the static coefficient times the normal force. We go to dynamic friction, we have sliding, we have dynamic friction. If it's not moving, we have the supports compressed together. This is static friction. Sometimes we start sliding and we have dynamic friction. So we have two different histograms of loads. In our analysis, we need to consider, yes?
As we know from Goodman rule and other criteria, for fatigue, we have also to take into account the static component of the load. In this case, why we don't take into account?
Because in fatigue, traditionally, in fatigue analysis in ships, we consider only the cyclic stresses and we apply the so-called Miner's rule. I consider that you know this. Miner's rule is based on SN curves and is the so-called damage accumulation rule. So you find how many cycles you have at certain stress level, divided by how many you need to have failure. So all this together, all these sums, we need to be less than 1. If you reach 1, you have a fatigue crack. So static component is not there. As a matter of fact, they say that the difference between the mean stress does not affect the fatigue line. Now, what you mentioned about the Goodman curve line has to do with when you have combination of stresses, like when you have bending and torsional shear stresses. But in this consideration, in evaluating structural details, in the context of Miner's rule, you do not need to worry about static stress. It is totally out, not considered.
Okay.
Of course, what we need to consider is the case of compression. If you have compression, for example, we do not have cracks that propagate in compression. If you compress something, you cannot have a crack propagating. But for conservative reasons, we do not consider the effect of compression in delaying the crack propagation. So all you need is to find the cyclic stress, go to the SN curve, you know, like there is a, we don't have a, can I write here, Leonidas?
Yeah, because
Where? Because this is a good question. So I need to explain this a little bit more. How can I
It
write?
will be better to explain by words due to the fact that we have also students from
So they
distance
cannot
learning,
see the.
so they cannot see the.
Okay. So
So
the
in
S,
order to be equal
understood,
for everyone.
understood. So the SN curve is a curve that shows how many cycles of a stress level S, how many cycles, say N cycles, at a certain stress level for failure. So the mathematical form of the curve is S times N to an exponent to a power of, say, M equals constant. This is the so-called SN curves that characterize a material like steel, like so this is what you use to estimate how much damage a component of stress will do to your structure. You take all these components together and you find how much you will have for X time, X years. When you reach the number 1, then you know you have a problem. But keep in mind that we make so many assumptions, and it's good to have some safety margin, some safety factor. Fatigue analysis is very uncertain. Personally, I do not like this method. I personally prefer to go with the crack propagation ideas. But this is what we are doing. For the same problem we have, it's complicated with the anti-rolling supports. There is a gap in the beginning. So in the beginning, when we have the gap, we consider the stresses acting separately for the supports and the structure. At some time, there's going to be movement and the contact between the anti-roll support and the structure, and we have different type of damage. The sum of the two will be assessed. Same with the cargo tank model. You see a cargo tank lying on the hull, on the double bottom, with the supports that we saw with the wooden supports. In this case, if we do not have contact between the supports and the tank, we have no force. So we like to know, do some iteration to see which supports are loaded in compression. The ones that are not loaded, we remove. So you realize that depending on the deflection of the ship, I will show you, we do not have uniform loading in all these supports. So to take the total number of supports, take the weight of the tank and the fuel, and split it in the supports is not a good idea, because we don't have a uniform loading. The loads are not balanced. And you see here two different deflection patterns. The red ones are loaded, and the other ones, the orange ones, are not loaded. So this means you have to do an iterative cycle. I'm afraid I have to show you, these are the critical areas that are typically loaded. And last but not least, I would like to tell you that God watches over children, fools, and people who try to do this type of fatigue prediction. It is a very uncertain process. Becomes even more uncertain because of the fact that fatigue life depends roughly on the cube of the stress. The cube of the stress. So if you are off by 10% in the estimation of your stress, then you are off in the fatigue life by 0.9 times 0.9 times 0.9. This is about 0.72, I believe, which means that you have a 30% wrong estimate if you do a 10% miscomputation of your stress. But besides that, and besides the conservatism and the uncertainty, we assume, for example, Weibull distribution for the stresses. Who knows if it's Weibull or something else? Still it works, and more or less we do not have fatigue cracks if we go through this motion. Now, the type C tanks, which you see here, they have the basic stuff that we are interested is their support compared to the that will be supported on the hull. These are called saddle supports. Usually we have two. We might have three, depending on the length. But it is recommended that we put only two. And one of the two also is free to move in the longitudinal direction, assuming that this tank is in the fore-aft direction. One of the two, preferably the one opposite the fuel connection, we leave it free. Why we do that? Because if this is connected with the hull rigidly, then the tank will follow the deflection of the hull. And we need to put additional loads on the tank. And I'm sure that the tank designer will not account for this type of loads. But we need to account for those. So we need to leave one direction fixed in the longitudinal direction and the other free to move. How do we do that? Well, you can have bolt holes that are elongated bolt holes, which of course you need in case of you put a cold liquid that is going to be, what is going to be when we put the cold LNG in the tank? We're going to have,
It's going to shrink.
exactly, contraction. We have contraction. So because of the contraction, if we don't have any thermal stresses if it's free to move. But if it's restrained, then we have additional thermal stress. So for these two reasons, we need to have one support fixed and the other free to move in the longitudinal. Now, how do we design it? We need to check backlink because we said that more or less the outside pressure is against vacuum. We need to check the impact. We need to check the operating pressure and temperature ranges. Residual stresses, in case we have welding, probably there is residual stress remaining. If the ratio of thickness to diameter is more than 1/20, we are dealing with a thick cylinder. The formulas for thick cylinder are quite different than the simplified ones of thin cylinder. The design thickness is the one that comes out from the formulas plus some corrosion allowance. Corrosion allowance also might be zero. If we don't have corrosive liquids like LNG is not corrosive. We don't need to increase the thickness of the tank. The stresses. We have three different types of stresses. We have circumferential stresses. Circumferential is because of hoop, like you have pressure inside, always we have a hoop stress. Anybody remembers the formula for hoop stress? Pressure times radius divided by thickness, PRT. Remember PRT. Then we have longitudinal stress. It is PR over 2T. It's half the hoop stress. And then we might have bending stress. If we have like the weight of the liquid and the tank itself, we have bending stress. In what direction? In the longitudinal direction. What is we consider the tank to be simply supported, and we start doing the bending moment. We find the bending moment distribution, then the stress in the tank, it is going to be the bending moment divided by the section modulus of the tank. And this is the formula for the moment of inertia for the thin cell. This divided by the distance from the neutral axis, which is in the center, will give us the section modulus. So we know the bending moment, we can compute it, divided by the section modulus, we find the longitudinal stress due to bending. We can also compute the shear stress. When we have bending, we have also shear. So shear, bending, hook, these are the stresses that we have. This is the system of stress. We need to design in terms of that. But it might be done three ways. One way is to do it through basic formulation. Some classification societies, most of these classification societies, have relevant guidance. The NVGL, Bureau Veritas, Korean Register, they have all the formulation, the formulas, the prescriptive formulas in their rules, so you can follow that. Or you can follow, and this is for a check, because the tank you buy probably from a tank maker. But it is good to check yourself. We have ASME section 8, ASME boiler and pressure vessel code. the EM standards, the British standard BS 5500, very thorough and very good standard. The Indian boiler regulation says boiler because we have pressure vessels. Of course, the IGF code, and also we need to apply the United States Coast Guard equivalency determination that has some criteria on how to ensure that there is equivalency with the heavy fuel oil. So either that or the universal panacea, the finite elements. You model the tank with finite elements. You don't need to worry about any of this, but some rules of thumb cannot be learned by finite elements. Finite elements is a brute force approach. You do a model, it's not a difficult model. You apply the loads and you find the stresses, and you know exactly where the critical stresses are. So the design steps is to select the material, find the thickness, determine the allowable working pressure, the minimum design temperature. Why the minimum design temperature? You know that at some time, as we reduce the temperature, we have the nil transition ductility temperature, NDT. This transition temperature is the one that below that we have brittle, occurrence of brittleness, and we lose ductility. Calculation of weight, calculations of the saddles, stresses in the saddles, the two supports that we saw, possibly utilize stiffening rings, and you need to consider the dimensioning. I will show you a quick way from ASME boiler code. ASME boiler code is not difficult to apply. It's practically diagrams and rule of thumb techniques. It's not difficult. It's easy. Same is true for BS 5500. Then we compute the nozzle and dome calculations. Nozzle is where we connect with the bunkering station. Dome thickness, possibly where the saddle goes, we put wear plates to reinforce. So the design calculations, I reproduced some calculations from the DNV rule, and we need to focus on the cell and head thickness. We consider the head separately because the shape of the head might be spherical or flat or tori-spherical. We'll discuss a little bit. So we do stress analysis, check buckling, fatigue, vibration, thermal analysis in case thermal stresses appear. First of all, every time we have two types of fatigue: high cycling fatigue and low cycling fatigue. Low cycling is when we don't have millions of cycles, but limited number, but higher stresses. So when we load the tank and unload it, we have thermal stresses coming up and down. So the design pressure is in general vapor pressure plus hydrostatic due to the hydrostatic effect, and inertia. Inertia pressure is the one due to accelerations from seakeeping. Where do you find the accelerations? In the guidelines, you will find empirical formulas that they will give you the acceleration in the longitudinal, vertical, and transverse direction. If you want to be fancier, input the lines of the vessel into a seakeeping code to compute those. Okay, the filling limit we discussed. So the formulation for the vapor pressure is given here as a function of the allowable dynamic membrane stress, which is 55 for martensitic and austenitic steels. Austenitic steels are the stainless steel. Stainless steel is called also austenitic steel. We utilize, a lot of times we utilize material which is stainless steel, because stainless steel does not appear to have nil ductility transition temperature. If you recollect from yesterday, if it was discussed, probably it was discussed that the material was stainless steel in the containment system. Why stainless steel? Because of that reason. Or 9% nickel steel, or aluminum. All these materials do not have transition temperature. So from this formulation you compute the vapor pressure. Then you have done the sea keeping, you have the acceleration ellipse, and you find the dynamic pressure, the inertia. Then you are ready to apply, having the total pressure, you are ready to apply the formulation, which for various types of tanks, the thickness is given by this formulation. We have the pressure, we know the tangential pressure, the membrane, allowable membrane stress, and we may or may not have corrosion allowance. Corrosion allowance is not necessary. It is between 0 and 1. The design itself is a whole lecture by itself. I'm going fast. I apologize, but I would like to give you an idea on where to find and what to do. I remember still my school days, what I was mystified to find out that in cells, in cylindrical cells, there is a discontinuity, there is an internal moment that is exerted at the junction between the head and the cylinder itself. The reason for that is that the deformation of this cylindrical cell is different than the deformation of this, and holding it together, modeling it as a beam in elastic foundation, you can find this internal moment. And shear, actually there is also shear, and this discontinuity needs to be accounted for in the computation of stresses. Here we discussed already that in collision we need to assess it by you putting half a g in the forward direction, and if the ship is smaller, we increase this to twice the acceleration of gravity. The pipe connections need to be mounted above the highest liquid level, except for tank type C. And if we are in a gas tight space, isolated from the rest of the ship, then the connections can be below the maximum liquid level in the tank. And we have connections, of course, for different operational reasons, like for purging, for emptying the tank, or for venting the tank. So we have many connections. Connections from below. You realize you have a limitation on where to put the saddles. You cannot put the saddles in the place of the connection. We might also have adjacent to the tank bulkhead, which need to be evaluated at the possible lowest possible temperature it might be exposed to because of an accident. The barrier, the secondary barrier pipe in double pipes also must enclose the welds in the connection nozzles. We protect. This is similar with the gas engines. The secondary barrier must contain the leakage of LNG for 15 days. Should not, if we have failure of the primary barrier, it should not impair the primary. The primary should not impair the secondary barrier. And if we have a failure of a support of a support or an attachment to the hull structure, this should not cause any loss of liquid in both the primary and secondary barrier. And needs to be able to be inspected, although this is not always possible. Please remember that we have also to check the static loads in case we have a static heel angle of the vessel of 30 degrees. Partial secondary barrier we have in tanks type B, the ones that are designed with leak before break, and they need to contain 15 days, the leakage for 15 days, and accounting for possible evaporation. Further design considerations is two types of fatigue, as we discussed, that if we have structural elements in the annular space between the outer and the inner ring, we need to increase their fatigue life. We need to design them for 10 times the fatigue design life of the tank. Why is that? Because they cannot be inspected. By the way, there is a special provision, should have special provision by the manufacturer of the tank to keep the vacuum. The vacuum and the insulation will degrade with time. There must be a provision that this vacuum will be preserved as much as possible. In the analysis we do, we have to consider the ovality, possibility of ovality of the circular shape. We said that we allow to have tanks installed below accommodation. This is an important consideration, especially for passenger ships. No passenger would like to see the fuel tanks on the main deck, the prominent deck. It is very critical during the fabrication to do series of tests. We need to trace the material, document the mechanical and chemical properties of the material, the construction material. And we need to do testing, NDT for the welds, and also pressure test, hydrostatic pressure test. We need to check the tolerances and make sure that if we do stress relief by heating, we can apply pressurization. This is acceptable. The hydrostatic test is 50%, the pressure, the test pressure must be 50% higher than the working pressure. So if the working pressure is say 10 bars, we pressurize at 15 bars. And the test pressure we maintain for every 25 millimeters thickness, 2 hours. So if we have the thickness of 50 millimeters, we maintain that pressure for 50 divided by 25 is 2, 4 hours. And while we do the testing, we have to verify that there is no obvious deflection of the tank. And if we calculate that the stresses exceed 75% of the yield strength, then we need to have prototype tank adjacent to the one we test with strain gauges and to monitor the stresses during the test. So testing during fabrication is really critical. So the inner critical inspection areas are the ones that are not accessible for inspection, like the space between the inner tank and the outer jacket, the outer tank. There is a leakage test which we apply periodically using helium. Now we discussed about different heads. There is the hemispherical head, the pink one, and then there is elliptical, 2-to-1 elliptical, and the toric spherical. Toric spherical is a combination of a sphere and the toroidal shape. The difference between them is that in the heads is that we gain more volume but at the expense of thickness. So the torus spherical head will require more thickness. It is the cell stresses that are higher in this type of heads. Type B tanks are designed with leak before break criteria because of their partial barrier, not the others. Type C are based on standards, recognized standards, and they do not need secondary barrier, and also practically it is a good idea to have leak before break criteria, but it's not necessary. Out of all this, tank type A and type B provide more volumetric efficiency. They give you more space to store compared to their volume, as compared to the type C tanks. Material we discussed already. Here is a proposed method to support. You might have three saddle supports, primarily for the vertical direction, to support in the vertical. But if you have three, notice that two of them have no constraint in the x direction. So in the x direction, I constrain only this, only the middle one. This is free to move in the x, free to move in the x. This to decouple from the hull. So the saddle support might be welded or bolted on the ship. This is one of the elements that we need to consider when we are preparing ourselves to install LNG system as a fuel. The insulation. The insulation can be various forms. Polyurethane, although flammability is an issue, we need to worry about flammability of the insulation. A very promising new technique is what we call aerogel, which we see here, aerogel blankets, and aerogel itself. Aerogel is a gel that we replace the liquid with gas. So this replacement creates aerogel with superior insulation properties. But what is much better is go back to heat transfer idea. If you have like two surfaces and you put this is what heat is transferred before, this is what is after. So we reduce, if we assume the same emissivities, we reduce the heat transfer with one sieve, we reduce to half. We put second, third, fourth sieve. You see why they are expensive. Because in a small space, we need to put these radiation sieves. The geometry. This is the saddle support, and this is the wear plate that we discussed. We reinforce, and this is the cylindrical cell. So imagine that this goes around. Rotate this 360 degrees. So this is the saddle support wear plate. Same idea for nozzle. Nozzle is connected to the wear plate, the reinforcing plate, with full penetration welds, not just fillet welds. Here you see a model. We call this area at the tip of the support the horn. It's the jargon of the terminology is that this is the horn of the saddle. So the finite element modeling will give you a very clear picture of the stresses. It's the brute force approach, and you don't need any formulation. If you really want to apply prescriptive formulation, I advise you to look in the internet, a paper written by Zick in the middle 50s, 1950s, which is still used today to design the cylindrical pressure vessels, and you can apply the formulation there and the ideas to do the design. Even Excel spreadsheets do exist that apply the Zick's method. There are simplifications where you can compute the natural frequencies of a saddle tank support combination. As we said, this is free to move, this is fixed, so this is like a cantilever with a mass at the end. You can find the natural frequency of such configuration and check if there is resonance with, say, the pitch frequency of the vessel. The saddle supports, where to put, one of the questions we have is where to put this support. This A dimension has to be at not more than 20% of the length of the vessel. This is a practical rule of thumb, but it works. And also has to be no more than half of the radius of the cylindrical vessel. These are practical questions, and this angle has to be between 120 and 150 degrees. The statical optimum is this bending moment with the terminology, the symbols are depicted here. This formula shows the bending moment at the support, and this formula shows the bending moment in the middle between the two supports. It will be interesting to do as an exercise, those of you that you like static, to prove that we have the best configuration when these two guys are equal. When this bending moment is equal to this bending moment. That's when we have, I'm sure with differentiation you can prove something like that. But this is when we have optimization. As an example, this is, for example, the longitudinal stress, and this is the PRT divided by 2. We said the longitudinal stress is half the hook plus the bending stress, bending moment divided by the section modulus. So we have a combination in the longitudinal direction of bending moment plus the longitudinal stress from the pressure. And this is what I meant by ovality. The regulations tell you when, if you don't have a stiff cylinder, then you might see this lack of circular shape. We have an ovalization distortion, and this is what you get. Some design data, just for reference. And you have to differentiate between pressure vessels and storage vessels. In our case, we're dealing with pressure vessels. The head shapes that we discussed, the toruspherical is a sphere and a torus. Since you are going to be prescribing stainless steel, I would like to show you this graph for reference. You can apply it in different circumstances. This is how different grades of stainless steel, which is going to be used, is the properties change. So in the direction of the arrows, the properties increase, like weldability, going from here to this improves, the yield strength increases, and also the corrosion resistance increases. Here are the properties. Here are the various grades that will help you to determine the most appropriate stainless steel and the most economical, because you can specify stainless steel 606, which is very good, but it's also very expensive. So you need to find a steel that will do the job, like 304L. I would like to ask you, just to break the ice, I have a quick quiz. We have a storage tank that is a double wall tank. inner, outer, and I would like to ask you, the inner tank is stainless steel. And I ask you if the outer tank, the red, marked as red, can be made from simple carbon steel. What is your opinion?
No,
It cannot be. Why?
because
Not just yes or no, justify.
yes, because we have two barriers for
Yeah.
safety reasons. If the first fails, that means that the second fails definitely. So we could have only one or two barriers from the same
Assume that
material.
the first barrier is actually so well designed that it will not fail. The answer is no, but
And
we
there is
cannot.
another problem.
Yes.
How to transfer the loads, the weight from the inner barrier to the support.
There are supports between the two. I did not show here. But
Yes,
if you
but
see-
they transfer also heat. So,
Correct.
so if the containment is cold, through the connection between the two barriers, also the external will be cold. So the carbon steel cannot is brittle at low temperature.
Okay. I will accept this explanation. Of course, the one I had in mind was that if you see these valves do leak. They are not tight. So if this valve leaks, we're going to see concentration of liquid LNG in the bottom of the tank connection space. In that case, the LNG will crack the carbon steel for sure. So we like to have the maximum degree of protection, and the red has also to be stainless steel. So you cannot have only the primary barrier in contact with LNG to be stainless steel. You need to be protected in the outside. This gives you an idea of the redundancy needs. We discussed about this. The stiffening ring, very easy. It's a rule of thumb with the codes. What you do, you assume certain, it's procedure VG20, UG28 of the ASME code. You assume a dimension for the ring that is appropriate for the tank. You compute the cross-sectional area of the ring, AS. On the basis of that, you compute this parameter, parameter B. Then you compute parameter A. E is Young's modulus, 2.1 kilopond per centimeter square, I think. Young's modulus for steel. And then you compute the required moment of inertia. This is the required moment of inertia associated with the ring of cross-section A. You can check if you have that moment of inertia. If you do, then you are okay. And in the equation, you need to consider also the distance between the span of the rings, how far away, because this is a critical parameter. Or you can use ready-made formulas for ring-stiffened cells, cylinders. Now, let's look a little bit on the cold box. In the cold box, we have the energy tank, we have the bunkering lines from the top and from the bottom. And then, in case we have reduction in the pressure, because the vapor goes, some LNG will come down from this line, and there is an evaporator. There is an evaporator which works with water glycol mixture from the waste heat of the engine. So this hot water glycol mixture will evaporate the LNG, and the vapor will be added at the top, keeping the pressure. This is what we call the pressure built-up unit. In the same heat exchanger, some LNG will evaporate and be compressed and go to the engine. So this is what the cold box contains. This is the cold box and the combination of fuel processing.
Why do we need to increase the pressure in
We do
of the
not
tank?
increase, we keep it. We keep it constant. We do not increase it. If you have boil off, if you have some fuel going out because you have vents and you have heat transfer from the surroundings, in that case the pressure will be reduced.
Okay.
So to keep the pressure constant, you need to put some vapors back. As you know, we have the state equation, which the state equation applicable in the case of LNG, appropriate state equation is Redlich-Von equation, but let's assume for the moment that it's an ideal gas, it's PV equals nRT. So if N is reduced, then the pressure is reduced. Volume remains the same, so almost the same, so we have to replace that N with the material, with the vapors that come from this heat exchanger. So this essentially is a dual, it can be separated in two different parts. From one hand, the first part of it, which is the last in the cycle of glycol water, will create vapors to replace the ones that have escaped, and the other part will create gaseous LNG to go to the engine, compressed and go to the engine. So it does have a dual duty.
Excuse me. In your LNG fuel vessel project, are there some ships using MGI engine? Or
Yes.
because I think this is only for LNG carriers, not for the vessels, the fuel engine, because the cold box is not applicable to be used as a fuel preparation room. So I just wanted to ask how do you arrange the fuel preparation room and tank connection room separately?
Well, this is the fuel preparation is in the cold box.
It means in your project also the high pressure pumps and something like that would be included in the cold box as well.
Yes, actually, this is could be another configuration to have also pumps, not only. I will show you different configuration. Here you see only the pressure built up. That shows you how to control the pressure. So from A to B you have static, hydrostatic pressure. From B to C we have subcooled LNG, which becomes saturated liquid. We heat it, so it becomes saturated, and then it becomes superheated from C to D, and that vapor goes on top of the LNG liquid to keep the pressure. So this has nothing to do with LNG carriers or LPG carriers rather. This has to be there, depending on, of course, on your engine. So in others, so this is the double wall fuel storage tanks. The tank connection space, annular space. Let me see. This is a different one where the two heat exchangers are separated. There is also a pump. There is a pump that takes the LNG and goes directly through the master gas valve to the engine. But let me proceed a little bit. There might be that the pump is inside the tank. inside the tank. This is for lower pressure with both two-stroke and four-stroke. These proposals come from Varsa. So these ideas are from Varsa. This configuration with the pump has higher maintenance cost and lower reliability because you have rotating equipment. Another one is again separate the two heat exchangers, but this is applicable only to four-stroke engines where the pressure is high. So depends on configuration that you are going to have, depends on the type of engine that we are going to use. The double wall storage tank has higher insulating capacity, but it's more difficult to make. So it is done in smaller sizes and like no more than 1,000 cubic meters. And also it is more expensive, evidently. The single wall has lower holding time, less insulating capacity, but it is cheaper and can be done in bigger sizes, like 2,500 cubic meters. It can be done. The fuel system, this is a proposal, for example. This is in containers, an example with containers. These are the tanks in containers, 40-foot containers. Then we have from here we have the heat exchangers with a glycol water heating medium from the waste heat of the engine, and then the fuel preparation with the compressor. This is an example, but it is very applicable to LNG fuel vessels.
So, excuse me, what I asked you before is whether how do you separate the fuel gas supply system from the tank and tank connection systems in your LNG fuel vessel project?
My
Yeah.
LNG fuel project.
I mean, you said you have a lot of projects like LNG fuel vessel. The design is quite new, so maybe there will be a lot of approaches to arrange of fuel gas supply.
What you mean structural?
Yes.
No specific pattern. You can. The main idea is to have as few gas hazardous spaces as possible. So if you can put everything in one space, this is the recommendation.
No. For energy engine, it is impossible because the high pressure pump should be included in the supply system. So it shouldn't affect the tank connection system and tank itself. If it is designed in the same area, jet code is not satisfactory. So
yes, and this is the you mean let me see. I have examples where there is following the vaporization, there is pump that these are all schematics, like here. The high pressure pump is outside the tank and it goes to the engine. Also, there is a pump inside the tank which might be used for LNG to the auxiliary engine. So this is an example.
Yes, there is feasible. Yes, but my question is where is the normal practice to put that pure gas supply system. I just could say the fuel preparation room. Where do you put normally on vessel?
You put it close to the tank.
Close the tank.
Yes.
Separate.
Because you can utilize the containment of the tank for this, but it can be under deck. It can be provided we follow the guidelines given here of ventilation up to 30 air changes,
Yes.
30 air changes an hour. If it's enclosed space, it is easy, but if it is and you can use the access that you're going to have is actually depends if it's from the main deck or not. I do not see any specific reason other than to categorize this as a hazardous area because gas can be present. But can be anywhere. Can be anywhere. I would put it close to the tank to avoid having long connection pipes because you might need to use, depending on your design, to use double wall pipes. And double wall pipes are very difficult to make. So, speaking of pipes, this is how they look like. They're made from stainless steel. The outer pipe also is stainless steel. The space between the pipes is inerted, and the pipes are supported by spring supports. Looking at the system from the main deck, what is in the open deck does not need to be in the open space, does not need to be double space. We see that every meter, about 90 centimeters, the red marks are spring supports for the inner pipe. Also, maybe depending on the configuration, we need the blue support, which is vertical support. If we look at it in a cross section, these are the spring supports, which are, this is the inner pipe, outer pipe, and the spring supports is glued polyurethane, polyamide material like a hose to avoid wear of the outer pipe. This does not require extensive maintenance, and we might need to do some purging. There is gas detector inside the pipe to detect if there is gas leakage from the inner pipe. The inner gas pressure is 7 to 9 bars. Inner gas used here is nitrogen. We discussed about ESD and gas safe design. Here, for example, we say if the fuel preparation room, which includes the pumping, if it is below deck, which is more or less the case, you're not going to see it in the main deck for many reasons, because green water might kill it. Then you must have an access from the open deck. Otherwise, you must have, if you don't have an access from the open deck, because it's a gas dangerous zone, you must have an air lock, as we discussed. In general, if you use an air lock, all the time you use it if you connect two different categorization spaces, a gas safe with a gas hazardous area. If you have inerted spaces, there should be arrangement that nobody will go and open the door to the inerted compartments because whoever enters will die. There is lack of oxygen. So we should make sure that nobody will inadvertently open the doors and go into the inerted space. These are the requirements for the ad hoc. There are a series of requirements. This comes from the IGF code. IGF code is available in the internet. You can download it, and it is not going to change, maybe with the exception of the location of the tanks. But I wanted to tell you about an innovative idea. I would like to tell you about an innovative idea on how to store the gas. All this costs a lot of money, and the solution probably comes from chemistry. Chemistry has advanced probably a little bit more than naval architecture. Chemists have created new materials. They are called metal organic frameworks. The metal organic frameworks are new materials connecting metal compounds with organic elements, and the characteristic that they have is that they have very high specific area. 1 gram of such materials has 1 gram, has the surface of 1 football field. It is amazing. So the bottom line is, if we fill a tank, an empty tank, with LNG, we have certain volume we can take. If we fill the tank with metal organic framework compound, I'm not going to tell you which one, but such a compound, no specific preference, and put material there, can fill much more gas than the empty tank, much more. And the gas can be released by just opening a valve in the tank. So the metal organic frameworks are like volume multipliers. So maybe in the future we are going to see them used for many different applications, like for example storage of CO2. Right now CO2 is out in the air. We might be able to store the CO2. Storage of hydrogen. Hydrogen, some of you I hear you work on utilization of hydrogen as a fuel in the future. Storage of hydrogen is much more complicated because hydrogen is liquid in minus 260 degrees, even lower. So it's very difficult to keep. What if you have a way to store it with metal organic framework? Methane. There are various solutions. And I would like to, finishing my presentation, I would like to tell you that it is not only LNG that is going to be used in the future. LNG will be the name of the game until 2030. After that, be sure that we are going to see different fuels, like, for example, methanol, other biofuels, hydrogen, which is probably the cleanest possible fuel. As Professor Theotokatos said, LNG engines do not comply with Tier 3. And Tier 3 is very difficult to comply with. EGR and selective catalytic reactor, it is not machinery that is easy to install or cheap. So unfortunately we satisfy the sulfur but not Tier 3 requirements for two-stroke engines. For gas engines it is okay, we satisfy NOx, but for two-stroke, no. So hydrogen is the cleanest fuel. Hydrogen plus oxygen, we get water. So could be a future fuel. Thank you very much for your attention. And I would like to tell you that this presentation aims to give you motivation to look further. It is not easy to cover such a wealth of material in such a limited time. So you have the presentation. It is available, Leonidas, right?
Yes. Yeah, of course.
You will have the presentation. Use this to take headlines, and look around a little bit more. The areas that you are interested. If you are interested in design, look more, and the field is continuously developing. We learn more things, new things. We're getting more experience. More things are developed. GDT worked this solution just recently, just the last 12 months. Before there was nothing. So continuous development. We have time for a few questions, Leonida.
Yeah, of course. Without,
Yeah, it is not so late.
and if there is any question from
And I appreciate your questions with the time.
Sorry for more cancel. This is a little different from the topic, but you know the new IDC code, right? And the filling limit has a little bit changed. So
Yes, the reference, the definition of the reference name.
yeah, right. Basically, we accepted 98.5%, but the approval of the flag government. But now
98%.
yeah, that is the IGC code approves 98%, but it was we accept the government approves the higher than 80%.
So your density was actually
yes.
a temperature lower than the loading temperature.
Yeah, yes, but you IGC code has some problem calculating this one because the vapor pocket when it comes to the membrane type vessel, the vapor pocket it should be confined in the spaces where the relief valve is not applicable. So that could be a problem to the accepted level. So have you thought that?
I have dealt with this issue extensively, and the only problem I see
Yes.
is how to go. What you know is the temperature of the sea and the temperature of the air. This is all you know.
Yes.
There are contours you can find in the internet. Air temperature for month of July, for the whole world. You know, other. You can split in blocks, in squares, and each square has a certain temperature for the air and for the sea. There are weather models that will give you that. So you know the outside. But then, what you need is to find the temperature of the LNG. So practically you need to do a model through conduction, to find out what will be the temperature of the LNG. This is the only difficulty I see. If I'm able to compute from the surrounding temperature, the temperature of the LNG, then I can convince the flag to accept temperature below 45 degrees, which is the limit. Because if I get 45, then I'm dead. Then the 98 will become 78. So this is the idea. If you get 98.5, you have to prove that you will go below. The LNG will be below but even that, I believe there is a limit. 98 is the limit. Cannot go above it. So 98 is the absolute limit. You can go below, but not above. And even just as a hint, for those of you that deal with stability, even at 98%, there is significant free surface correction. So for stability purposes, it's important. Another thing we did not discuss was the orientation of the tank. The tanks are usually horizontal, but they can be vertical as well. Vertical will save us a lot of space, but if they are vertical, we have stability for them. So we need to make sure that we're not going to capsize the vessel because of negative metacentric height. Also, the other thing is how to support the vertical tank. It's not easy. It's more difficult. The sample supports is easy. Do we have any questions, Leonidas, from the
Spontanea? As I can see from here, no, but you can ask them also. Let's see. This one. So you can ask them.
Is there a question from the
Spontanea?
Spontanea?
No, thanks, no thanks. No questions. Okay. Okay. So
We appreciate your attention and patience with the schedule. Thank you. Anybody else from Strathclyde? Good, that means it was a very thorough presentation. It was tough for me, but I'm going to repeat this presentation a little bit more compact at the SICTO meeting, Mediterranean SICTO meeting. SICTO is the gas association. They deal with LNG as fuel and also LNG carriers, LPG, LNG. So they have a meeting in Athens, I believe September.
Okay.
So I propose to them that I do a similar presentation, but a little bit more compact because I have 20 minutes.
Okay.
So it has to be much more focused. But in general, it's a lot of rules and regulations and materials, and you realize that you have to know practically every aspect of it. That's not easy. If you cannot know only structures, or only thermodynamics, or only mechanics, you have to know everything practically to do a good job. This is the fate of the designers. Designers, besides having a feeling, they need to know everything. It's not easy.
And what is the maximum size of independent C-type tank?
Very good question. If it's single, I think you can find in the presentation. If we're talking about LNG fuel, right?
Yes.
Because if we're talking about LPG carriers, which use various types, and they do have bi-lobes. Bi-lobe tanks are like two cylindrical tanks put together. The good value will be 2,500. Yes, but only for single wall. Double wall is no more than 1,000. So imagine cubic meters. Now, what is the density of LNG? Density of LNG, I believe, is 0.645, something like that. 0.6 is the first decimal point. So if you have 1,000 cubic meters, M equals density times V, so it's about 600 tons, not much. So you need a lot.
It sounds the independent type C is not applicable to real fuel large size container vessel. We have to find the application of
Container vessels, you are going to lose some capacity of carrying
but we need a lot of cylinders.
Not a lot. You don't need many containers. But where you're going to lose a lot is in what are you going to do in emergency? That's where you have to start considering membrane tanks, type A, type B, and people change. Last October, I was in London at IMO meeting, MEPC 67, and there we had a discussion by United Arab Shipping Company from Kuwait, which discussed very proudly the fitting of LNG as fuel in their container ships. And they used independent type A tank. Now I hear from GDT they changed their opinion. They are going to go with membrane tanks. Because membrane tanks are more expensive but appear to make better space utilization. Unfortunately, all this can collapse as a paper tower if there is a reverse of opinion for the location of the tanks. Because membrane tanks are practically 760 millimeters away, 800 millimeters away from the side set. So what are you going to do if they say no, minimum B over 5? Then you cannot use it. So it will depend on the location of the tanks. Now, to the best of my knowledge, both approaches are going to be applied. Probabilistic and deterministic.
I'm sorry, last question. How did it end up with the provision of the risk assessment in IGC code? Is there the previously the risk assessment is a mandatory requirement for every LNG fuel vessel, but it's still controversial, right? How did it end up?
It is mandatory. For the LNG as fuel, risk assessment is mandatory.
Okay, for every ship.
For every ship.
Okay. So is the class approving the risk assessment?
Yes. By the way, I'm not a strong believer of risk assessment. This is my secret. But I'm not a strong believer, but it is the big lab of classification societies. If you remember, goal-based standards, GPS, they go and explore new areas where there are no regulations, no prescriptive rules. To protect ourselves, we have devised the risk assessment, but this is something that we do anyway. I mean, as a designer, aren't you going to sit down and identify the risks? The first thing that you do in a risk assessment is to identify the hazards, hazard identification. First step. A lot of times it's not one person, but many persons. They do it together. I believe it is necessary and people do it anyway. The second step, hazard mitigation. What can you do to make the risks low? This you do anyway. If you call it risk assessment, fine. There is qualitative risk assessment and quantitative. And this is where I have my objection. The quantitative risk assessment. How do I know that the risk is so much? Probabilities. There is a database out of which we take the quantitative risk. Okay. I see Leonidas standing.
No, you can continue. Just the availability. I would like to check for Mr. Protocatus in order to have a last session. You can continue and
Okay,
if you have
okay.
any more questions, you can.
Other questions, not necessarily on this topic. Other topics, like the harmonized structural rules, maybe EDI, maybe minimum power. I am in an environmental panel of IEX, so I deal with these issues.
About the inspection, actually, because it's my topic for my individual project.
The rules is similar with other ships or is more strict? I haven't seen any rules specific for LNG ship yet.
Take, follow the philosophy. If you want to become fancy, follow philosophical approach. One critical is the inspection schedule, how to do it. There is a school of thought, you know, the bathtub idea, eh? The bathtub.
Exactly.
In
And
life,
the
we have
critical
bathtub.
areas for cracks.
So that means to me that in the beginning of life, the cradle stage of life, the baby phase, we do a lot of inspections. We don't split every 1 year, every 2 years, every 3 years. No, this is a mistake. The uniform space. We increase the density. In the beginning, we inspect more, and then we do it in larger spaces, and towards the end of the life, the upper part of the bathtub, we also increase because, and we see this in the rules, the ESP regulation. ESP notation is Enhanced Survey Program. ESP, after 15 years of age of a ship, we do more inspections. In the beginning, no problem. This is why we classification societies give no fees in the beginning of their ships' life, because inspections are easy. They pay no money.
Are you from field or?
Field. Now, yeah,
It's a completely different question. Yeah.
different.
All right.
I don't know if we are replied to your.
Yeah.
But if you need specific inspection for LNG ships, it's easy to find. All classification societies.
Yeah, I've seen these rules, but I haven't studied particular for LNG how to inspect.
The critical areas for LNG, you know, as you know
Yeah.
for every ship, so you go and focus there.
So during the last few years and during the years to come, it's sort of a race, and on the one side there are the regulations with which the ships will need to comply, and the egg areas and all that, the EDI as you mentioned, and on the other hand is of course the financial part and finding the right balance between the expenditure and compliance with the rules and saving money. Do you believe that? How do you believe the LNG fueled vessels stand in between the other their opponents, let's say, as proposals in this situation?
You mean the LNG carriers or the LNG fuel?
The LNG fuel vessels. I mean, how viable do you think this solution is, not only for the passenger vessels, but also for cargo vessels, for tankers,
For passenger vessels, it's very viable because they have specific route, so they can have bunkering at certain points, point A, point B. So it is fixed route. They know the time, they know everything. They are routine time, so it is easy. Others, they can plan accordingly and be viable. What is the motivation behind looking at LNG as fuel? There are many reasons. One is environmental friendliness. The other is efficiency, clean combustion. We can discuss, probably you discussed already in this training session. But the most critical aspect is price and availability. This is really what gives you a very good prospect for LNG. Wherever we stand, we have reports that we had discoveries in Qatar, in America, the shale gas. So if we are going to have shale gas, of course we are going to have LNG as fuel. So there is very good prospect regarding availability. price at this point is very uncertain because in America LNG is cheap. You go in Korea, it is very expensive, isn't it? It's very expensive because in Korea they carry, so it is not the same. It will probably stratify. So if I go to Korea or to Japan, Japan is also, they are expensive. If you go Korea or Japan, maybe you don't bunker there, you bunker in Qatar. So this is a consideration in the design of your storage tanks. You need large tanks to have a lot of fuel. So you don't have to bunker every 1,000 miles. But overall, it appears that LNG as fuel is very critical. We have been asked a lot of questions. Unfortunately, as you all know, the majority of cargo vessels, which is bulk carriers, is suffering right now. They are in big trouble. I'm afraid many companies will be out of business if this low freight rates continues. Tankers still have a lot of work because of the low price of oil, which encourages building up of tankers. But I'm not in large despair because some people do build tankers, bulk carriers right now. They build Kamsarmaxes, they build, so everything depends on a techno-economic consideration. Before you do this work, you have to do a study and see what is preferable, like utilize scrubbers, utilize distillate fuels, to comply, something to comply with everything does not exist today. Like hydrogen is very far away. Somebody wants to show. But there is a very good prospect for LNG vessels, LNG fuel vessels. From Greece.